So today we're going to look at the mole. Finally, we get to learn about the mole. The mole is probably one of the most important numbers in chemistry and concepts in chemistry. You'll use it all the time. It literally is the Rosetta Stone for chemistry. So if we review back to atomic mass, we talked about this earlier. Remember that atoms are so small we can't measure their masses in pounds or kilograms. We actually had to come up with a new unit, and we called that unit an atomic mass unit. We use the units AMU or the Greek letter mu. And what does that mean? Well, that number is, 1 AMU is 1.67 times 10 to the minus 24 grams. So it's like a super, super small number, like ridiculously small. And we have that value on our periodic table. So one carbon atom weighs 12 AMUs. Now, remember that we have chemical formulas. We've been dealing with those all along. And a chemical formula just tells us the number of atoms of every element in the chemical, in the compound. So, for example, here is the chemical formula for aspirin, C9H8O4. So to have aspirin, you need 9 carbon atoms, 8 hydrogen atoms, and 4 oxygen atoms. Remember that, I always go off on a tangent with this, but aspirin is just a chemical. So it's a certain chemical that doesn't matter what brand of aspirin you buy. If it's the aspirin type of pain reliever, then you can buy generic or whatever. It is this chemical, and that's what it is. So it doesn't matter which type or which brand you buy because it is a chemical. But that's what makes it aspirin. It's the way those elements are put together, and it's the way those chemicals are put together and the number of atoms of each element that are in them. So, a little bit of notation here. Understanding the words molecules and compounds. So, we're going to be a little bit more specific now this year because a molecule and a compound are kind of different things. So up until this point, we would say a molecule is just a group of atoms and a compound is a group of atoms, and they have to be different. These words actually mean more than just that. Molecular compounds, molecular or molecules, are usually things that are formed by covalent bonds. And ionic compounds or compounds are usually ionic. So when we talk about water, you don't see me talking about water compounds. We call them water molecules. But we don't really say molecules of salt because a salt is, it's a compound. So we actually use the word formula units. And that's what I'm saying here. So you can have water molecules, but we don't really ever have salt molecules. It's not the way chemists speak. We would actually call them a formula unit of salt. So it's like the smallest piece is just an NaCl. It's the unit of the formula of a unit. Anyways, now that we've kind of separated those two terms, we can talk about molecular mass and formula mass. Now, both of these are really the same thing, but one is for ionic compounds and one is for covalent. So molecular masses is the sum of the atomic masses in a molecule. So that means that they're covalent. Really, the terms are interchangeable. Lots of people will just call it they'll always say molecular mass, but in this course or in any course, it's probably good to understand the difference between the nomenclature, the way we say things. So what is molecular mass? It is the mass of all of the elements in the molecule or compound. So in this case, we want to talk about, like, we know that carbon weighs 12. Well, there are 9 carbons, and each of them weigh 12. So I'm going to go 9 times 12. And 8 hydrogens. So I'm going to go 8 times hydrogen weighs 1.01. And there are 4 oxygens, and each oxygen weighs 16. So if we want to talk about the mass of an aspirin molecule, we're going to take all those numbers and add them up. So 9 times 12 plus it'd be 8.08 plus 4 times 16 is 64. So I get 180.08. And since we're talking about one molecule and we're talking about atomic mass units, it's AMU, or the Greek letter mu, which is fine. Now, a formula mass is the same idea, but now we're just talking about an ionic compound. So it's the same thing. So if we're talking about like sodium sulfide, this is ionic because you have metals and nonmetals. If we want to find the mass of this compound, we would say that there are 2 sodiums, so 2 times, and we look up sodium, and it should be 23 AMUs. Oops, 23. And sulfur, there's only one of them, so it's 32.1. So 2 times 23 is 46, and 32.1 should be 78.1 AMUs. Let me just double check that. Times 2 plus 32.1. Yes. Okay. So that's how we do formula mass and molecular mass. Now, oftentimes, and this is what I'm saying here, I don't want to get lost of the molecule or compound. But just know the word molecule or molecular is usually referring to covalent, and formula units or compounds are usually referring to ionics. So, finally, the mole. Now we can talk about what the mole is. And if we're talking about trying to, like, let's go back to this. If we want to weigh that much, it's still such a small mass that we can't weigh it. We don't have a scale that's sensitive enough. It's just not possible. It's way too small. But what we can do is we can weigh, so like this would be the mass of one molecule. So if you thought about this, if we had 2 molecules, or 3 molecules, or 1,000 molecules, or 10,000, or 1,000,000 molecules, that mass would be getting bigger and bigger and bigger and bigger. And eventually, we would get to a point where the mass is something we can actually measure. And we can't measure AMUs, but we can measure grams. So it would take a certain number of molecules of aspirin, for example, to weigh that many grams. If we wanted to have Na2S, it's going to take a certain number of molecules to weigh this many grams. I'm going to use that number. Let's talk about 78.1 because that's the molecular mass of this compound. But I can't weigh these, but I can weigh these. So if I have enough of these molecules or formula units, whatever you want to call them, if we have enough, we'll have that same number, but in grams. So in other words, we need a huge pile of them. And the pile that we talk about just so happens is what's called a mole. It's a unit that's used to describe enough atoms to equal the atomic mass in grams. What the heck does that mean? If we have eventually, and like let's say one carbon atom, I think I have it on here, one carbon atom weighs 12 AMUs. Okay? If we have enough carbon atoms, lots of carbon weighs 12 grams. I'm going to put atoms here. Now, it's going to take a ridiculously large number of carbon atoms to get to 12 grams because these are so light. Only 2 carbon atoms would only be 12 or 24 AMUs, and 3 would be 36, and so on. To get to 12 grams, it's a huge number. Like, this number is huge in comparison to 12 AMUs. That's a huge unit. It's like the difference between light years and millimeters. But if we're talking about particles and atoms and molecules, these things are so small that we need to be able to have enough of them that we can measure them, and that's what the mole does for us. It's designed to be like a multiple, like a convenient multiplier, like a dozen. So like you go to the store, you don't buy one egg at a time, we buy dozens of eggs. If we're talking about going to buy Timbits, we buy them not usually by the single Timbit, but we'll buy them by dozens of Timbits, or donuts, or whatever. So we can't measure AMUs, is what I'm trying to say. Here's an example for sugar. Sugar, a molecule of sugar, if you add up all those masses, it weighs 342.34 AMUs. But we can't measure that. Even though that's a big number of AMUs, it's still too small to measure. But we can measure 342.34 grams. So the number of molecules it takes to have that many grams of sugar is what we call a mole. And there's a video here that I'll link to later. But basically, that's what a mole is. And it works like this for every single element, molecule, compound, whatever. So it's the same as, so if we're talking about molar mass, it's the same as formula mass, but now our units are grams per mole. And the formula mass or molar mass of any compound is the mass of 1 mole of stuff. So like the sugar above, or the 12 grams of carbon. So 1 carbon atom weighs 12 AMUs. A huge number of carbon atoms would weigh 12 grams. It just so happens that the number of carbon atoms and the number of sugar molecules to weigh those masses happens to be the same. And that number is 6.02 times 10 to the 23rd. And that's what we call Avogadro's number in honor of Amedeo Avogadro, who came up with the idea that, this number would exist. He never did actually determine the number. Other chemists have come along and figured it out. But he had the idea that if you had certain amounts of things, that you would have the equal number of particles in those. Now, we're not actually sitting down and counting atoms. There's lots of different ways to determine this. But time and time again, we've determined that if you have 12 grams of carbon, it will be the exact same as what would be 16 grams of oxygen in terms of the number of things you have. So if you have, let's talk about salt, NaCl. If you add up Na23 plus Cl is 35.5, so this would be 58.5 AMUs. That's the mass of one salt molecule or unit, if you will. If you have 1 mole of it, it would be 58.5 grams. Well, if we did the same thing for water, H2O is equal to 1.01 times 2, because there are 2 hydrogens, plus 16, is 18.02 AMUs. Well, if you wanted to have a mole of water, it would, this is what 1 molecule weighs. 1 mole would weigh 18.02 grams. And if you actually looked at the number of things you had in each of those masses, it would be equal to this number. You'd have this many salt molecules, if you will, using air quotes there, and this many water molecules in 18.02 grams. It gives us sort of a way to work with these numbers, and it actually allows us to talk in the amount of stuff rather than just molecules. So now I'm just going to erase what I have here so you guys can see this better. So again, if we have carbon, hydrogen, methanol, whatever, doesn't matter. If you have 12 grams of carbon, you have this many carbon atoms. If we're talking about hydrogen gas, H2, it weighs 2 or 2.02 grams. If you have that many grams, you have the same number of hydrogen molecules. And if we're talking about methanol, this is CH30S. So if we weigh that, you add that all up, it's going to be 32 grams. If you had 32 grams, you have that many methanol molecules. So really what we're doing here is exactly the same thing as formula mass or molecular mass. Instead of talking about the mass of 1 molecule, we are talking about the mass of a mole now. So our units actually become grams per mole. So this is what it should look like. Magnesium. If we look up magnesium, magnesium weighs 24.3, and carbon is 12, and oxygen 3 times 16. So when I do this, let's do the calculator, 24.3 plus 12 plus 3 times 16 is 48, 84.3. If we were talking about a molecule of this or a single unit of this, it would be AMUs. But we're talking about a monstrous pile of them, a mole of them. So our units are now different. The units are grams per mole. And that's actually where the word mole comes from. It's from like the Latin or Greek word for a huge pile of stuff, a large amount. So that's basically what it means. It just means you have a mass of a pile of these molecules or compounds, whatever it is. So let's do another one. Calcium phosphate. So when we're doing calcium phosphate, we need 3 calciums. So 3 times calcium is 40.1. Plus, there are 2 phosphoruses. So 31 times 2. And there are now 8 oxygens. So 8 times 16. So when we add these all up, so 40.1 times 3 plus 31 times 2 is 62 plus 8 times 16. I get an answer of 310.3. And if it was a molecule, if we were asking for just how much does one of these things weigh, the unit would be AMUs. But now our unit, because we're asked for a mole of them, a huge pile of them, would be grams per mole. So it's the same process, just the units are something we can actually work with and measure now rather than just dealing with units that we can't.